Have you ever noticed how some numbers just, I don't know, they just seem to fit together perfectly? Well, today we're going to dive into a pretty fascinating numerical mystery. We're exploring a special class of numbers that holds a really unique geometric secret.
This idea goes way, way back. For thousands of years, thinkers like the Pythagoreans believed that numbers weren't just for counting stuff. They thought they were literally the building blocks of reality. They saw patterns in everything, and they were convinced that if you could just decode those patterns, you could figure out how the whole world works.
So that brings us to our big question. When we talk about a perfect square, what does that even mean? What gives a number this special status?
Take a look at this sequence of numbers. 1, 4, 9, 16, 25. Do you see the pattern? I mean, visually, it's pretty clear, right? Each one is just the result of a number multiplied by itself. You've got a 1 by 1 square, a 2 by 2, a 3 by 3, and so on. This visual is really key to understanding the whole thing.
Okay, so let's get right into it. What exactly makes a number a square in the first place?
And the idea is actually, beautifully simple. A perfect square is just any whole number that you can arrange into a perfect, physical square shape. The number itself literally becomes the area of that square.
Okay, check this out. This visual really nails it. If you have the number 9, you can arrange 9 blocks into a perfect 3 by 3 square, no problem. But try it with a number like 30. You're always going to have leftover blocks or an incomplete shape. So the question is, how can we test this for any number, even a massive one, without having to draw little blocks every single time?
Well, it turns out there's kind of a secret code hidden inside every single number that gives us the answer. We just have to know how to read it. And we do that using something called prime factorization. I like to think of prime factorization as finding a number's unique DNA. It's really just the process of breaking a number all the way down into its most basic building blocks. Those are the prime numbers that when you multiply them all together, get you right back to your original number.
And the easiest way to do this? A good old-fashioned factor tree. You just start with your number at the top, you branch it out into any two numbers that multiply to make it, and you just keep branching down and down until you can't go any further, when all you're left with at the bottom are prime numbers. All right, let's actually try this out. We'll use that factor tree method to test the number 36.
So if we break down 36, we could start with, say, 6 times 6. Then we break down each of those 6's into 2 times 3. Now, since 2 and 3 are both prime numbers, we stop right there. And there you have it. The prime factors, the DNA of 36, are 2 2's and 2 3's.
Okay, and this is the secret rule. This is the whole test right here. For any number to be a perfect square, every single one of its prime factors has to show up an even number of times. Not just one of them, all of them. To put it another way, every factor needs a partner. Look at 36. We have a pair of 2's, and we have a pair of 3's. Every factor has a buddy. That's the signal, that's the green light that tells us 36 is, without a doubt, a perfect square. It passes the test. Okay, so we know how to spot a perfect square. But what if we want to go the other way? How do we find the original number that got multiplied by itself to create the square in the first place?
Well, that's exactly what a square root is for. It's the reverse. If the perfect square is the area of our shape, then the square root is just the length of one of its sides. Simple as that.
Let's put this into a real-world scenario. Imagine you've got a square computer case, and you know its total surface area is 144 square centimeters. To figure out how long just one side of that case is, all we need to do is find the square root of 144.
And the answer? The square root of 144 is, of course, 12. Because 12 multiplied by itself, 12 times 12 gets you 144. So the side length of that case is 12 centimeters.
Now I know what you might be thinking. Okay, that's a cool math trick, but where would I actually use this? Well, this relationship between a side length and its area is all around us.
For instance, if you know a square picture frame has a side of 17 centimeters, you immediately know its area is 17 times 17, which is 289 square centimeters. And it works the other way too. If you know a square garden plot has an area of 196 square centimeters, you know each side has to be 14 centimeters long.
So here's the bottom line, the really crucial point. This isn't just about some abstract numbers. It's a fundamental relationship in geometry. Understanding squares and square roots lets you instantly connect that one-dimensional measurement of a side to the two-dimensional measurement of its area, and right back again.
Okay, you've seen the pattern, you've learned the secret code, you've seen how it all works in the real world. So, you ready to put it all together for one final challenge?
All right, here we go. A square picture has an area of 169 square centimeters. The question is not what the side length is, but what is the perimeter of the picture? See, this one requires one little extra step. So think about it. You've got all the tools you need to solve it.